Machines with moving part give rise to vibration and consequently noise. The setting up and the status of each machine yield to a particular vibration signature. Therefore, a change in vibration signature due to a change in machine state can be used to detect incipient defects before they become critical. This is the goal of condition monitoring, in which the information obtained from a machine signature are used in order to detect faults at an early stage. In general, the basic condition monitoring process is subdivided into three main steps. The first one being a relevant physical quantity, that is, our raw signal, is measured. Then the collected data are processed and the machine state features are extracted. Finally, the extracted state features are compared to the reference values. The signals are obtained through the sensors. The sensors which we are using is accelerometer. The interfacing device is NI module 6221, which is between sensors and the computer and is connected through USB port. Software used is LabVIEW. So what actually is a rotating machine? As you can see over here, it consists of three parts: the inner race, the balls and the outer race. The accelerometer is placed over the outer race and the signals are obtained. During the bearing operation, wideband impulses are generated when roller passes over the defect at a frequency determined by shaft speed, bearing geometry and the defect location. Some of the vibration modes of the bearing and its supporting structure will be excited by the periodic impulses and a distinct bearing signature will be generated. The leading edge of each impulse typically comprises of a very sharp rise that corresponds to impact between a roller and the defect. The ringing then decays with an approximately exponential envelope as the energy is dissipated by the internal damping. Applying Fourier transform to this type of signals result in a peak at impact frequency along with the harmonics due to the spike resonant nature of the signal. But Fourier transform cannot be used as it cannot be applied on non-stationary signals and the time information is lost. Many researchers have used short-time Fourier transform to overcome this time information problem, but low-resolution problem exists in STFT. These problems can be overcome by using wavelet analysis, which provides multi-resolution in time frequency distribution for easier detection of abnormal vibration signals. Now we will look at the different signal processing techniques. The first processing technique is fast Fourier transform. The Fourier analysis expands signals or functions in terms of sinusoids. It reveals all frequency components present in a signal. But this method cannot be used as it does not reveal time information. In addition to this, fast Fourier transform cannot be used for non-stationary signals, the signals for which frequency vary with time. These limitations can be fulfilled by use of STFT, that is short time Fourier transform. Now what is short time Fourier transform? The thing is, this provides the time and frequency relationship, which is the major advantage if we compare it with the Fourier transform. Basically, we need to segment the signal into narrow time intervals and then take Fourier transform of each segment. As you can see, the window is moving, the window of fixed size, it moves at the different time frequencies. For each time location where the window is centered, we obtain a different Fourier transform. Each Fourier transform provides the spectral information of a separate time slice of the signal, providing simultaneous time and frequency information. Short time Fourier transform. In this, window should be narrow enough to show that the portion of the signal falling within the window is stationary. As the window size is fixed, we will use wide window, then we will get good frequency resolution but poor time resolution. And if we use narrower window, then good time resolution is achieved but frequency resolution in that case is poor. To resolve this resolution problem, we go for the wavelet transform. So the major difference between wavelet transform and STFT is that in wavelet transform we can use the variable length window. So we will be using narrower window at high frequency for better time resolution, and we will use wide windows at low frequency for better frequency resolution. So wavelet transform is actually an effective tool to deal with non-stationary signals such as vibration signal waveforms. It offers simultaneous interpretation of signals in both time and frequency domain. Wavelet transform can be continuous or discrete. The continuous wavelet transform reveals more details about a signal, but its computational time is enormous. For most applications, however, the goal of signal processing is to represent the signal efficiently with fewer parameters and less computational time. The discrete wavelet transform can satisfy these requirements. The discrete wavelet transform computes the wavelet coefficients at different discrete intervals of time and scale. The computed DWT coefficients can be used to form a set of features that unambiguously characterize different types of signals. So, what actually the wavelet transform algorithm is? The dilation function of the DWT was represented as a tree of low and high pass filters, with each step transforming the low pass filter into further low and higher frequency components. The original signal is successively decomposed into components of lower resolution, while the high frequency components are not analyzed any further. The low frequency components of signals are called approximation, while the high frequency components are called details. This is the two-level resolution. The practical thing, over here we are using formula control instead of the DAC assistance. This is just to check whether the simulation part is working properly or not. As you can see, we have multiplied two sine signals and we have added a spike at time interval 0.1. So we are getting that spike over here, and with this we can also use a tap control, and we can give another thing, that is DAC control. We can switch it on to DAC and formula control at the same time, and we can check the output of it. So what actually we are using for the DAC assistance is that we are going for accelerometers, that is our sensor. So that accelerometer we are interfacing with NI6221. The real-time application accelerometer in the industrial purpose use costs around 30,000. So we have not used that one. We have just purchased a low sensitive accelerometer that costed 800 rupees. And the DAC assistance interfacing device which we used is NI6221. It is a 16-bit resolution which contains anti-aliasing filters, and through this we have achieved the output. This is the algorithmic concept. What actually we are doing over here, you can see that NI9233 is there. Instead of this we have used NI6221. Either way we can use any of the interfacing device, and the sensor will be accelerometer only. So what actually fault detection, how we have seen that fault detection, we can check it out. Our approach is actually based on the fact that cracks are translated into transients and high frequency phenomenon in the vibration signal. DWT decomposition is applied to the vibration data for normal and abnormal bearing using mother wavelet debachis. Extensive experiments have showed that the third level decomposition is sufficient for the problem of the fault detection. Hence, we can avoid expensive schedule-based maintenance by using DWT method. Here you can see this is the front panel of our program. It consists of raw signal, the FFT output and the STFT output. So this is a formula raw signal which we are giving from the formula node, and this is the DAC assistance, the whatever input we will get through the accelerometer. In the page 2 we are having the 3 resolutions of wavelet transform. We can switch here from DAC control to formula control. Formula control we are using just to check the simulation thing, and it's kind of a prototype. You can add anything over here, like if suppose we run this program, you can see the raw signal which we are getting through multiplying the two sine signal. This is the FFT output of it, and this one is the STFT one, the below one. So if suppose a spike has to be detected, and suppose it is present at time 0.1, then we can add over here itself spike of 0.1. So when we reset it, we can easily see that we are getting at 0.1. So it's not needed that you have to connect the DAC control for checking your simulation. So you can just go over here in the page 1 stuff, and you can check what actually your raw signal is, the FFT you are obtaining through it, and the STFT of it. These table give the RMS, the curtaces value. So while you are checking it out, it's seen easily that the wavelet transform is the best technique to detect a fault when you are going for wave signal processing. We can change it to DAC control and check it out the real-time application too. As you can see the initial setup, there is an accelerometer and a NI9221 module which is used as an interface between the computer and the accelerometer. There are lots of wires in that shows the two or three axis of accelerometer, and here the normal generation of the signal is there. We are having two options, either DAC control or the formula control. We can switch over it. So as we have already seen the formula control, now we will go for DAC control. We have to give the initial setups like the choosing of the channels. Now we have to build the VI. So after the building of VI, we will see the output of it. We just have to run the program, and after that you can see the raw signal, and this is the variation which we are getting. This is the FFT output of it and the STFT too. So while we are moving the accelerometer, there is a certain change in it, so that we are acquiring, and whenever there is a knock, we can get the knock too, the desired knock actually. So